There is a wall around you right now. You cannot see it, touch it, or travel to it. No spacecraft will ever reach it, and the closer you get, the further it retreats. And yet it is absolutely, undeniably real. It defines the total territory of everything you will ever know, everything that can ever reach you, everything that can ever affect you in any meaningful way. Beyond it, things are happening right now. Stars are being born, galaxies are colliding, perhaps civilizations are rising and falling, and none of it will ever reach you. Not because of distance, not because of the limitations of our technology, but because of a hard limit baked into the structure of reality itself, written into the fabric of the universe the way a speed limit is posted on a road. Except this one is enforced without exception, without loopholes, and without appeal. You are sitting inside an invisible bubble approximately 93 billion light-years across, and in the most important sense imaginable, that bubble is shrinking. Not in absolute size, it is actually growing in one dimension, but it is shrinking in the dimension that matters most. There are galaxies right now, real galaxies with real stars and real planets, and perhaps real life, that are already beyond the reach of any information, any signal, any photon we could ever send their way. Not just unreachable by current technology, unreachable in principle, now and forever. They are not merely far. They are causally severed from us, permanently and irreversibly, by the expansion of space itself. The edge of what you can see, the edge of the observable universe, that famous 46 billion light-year radius, is not actually the most important boundary. There are 3 distinct walls around our existence, and they are nested inside one another like concentric prisons, each more final than the last. The observable universe is the outermost one, the furthest distance from which any light has had time to reach us since the Big Bang. Inside that sits the cosmic event horizon, the boundary beyond which we can never receive any future information, no matter how long we wait. The event horizon is currently only about 16 billion light-years away, considerably closer than the observable universe, and it is not growing. It will stabilize at perhaps 17.5 billion light-years, and then everything beyond it recedes forever. And there is a third boundary still, the affectable universe, the region within which anything we do today could conceivably have any future effect whatsoever. Beyond that, total causal silence. Now here is what makes this genuinely, profoundly unsettling. We tend to think of limits as temporary things. Build a bigger telescope. Wait long enough. Aim your instruments somewhere new. But these limits are not temporary. They are not engineering problems. They are physics. The universe is not just large. It is actively working to reduce what we can know. Dark energy, the mysterious force accelerating the expansion of the cosmos, means that every year, every decade, every century, more of the universe crosses the event horizon and becomes permanently unreachable. The number of galaxies within our cosmic event horizon is slowly falling. We are being walled in. And we have only, in the last few decades, begun to understand what that means. The cosmological horizon is the most profound physical boundary ever identified by science. It is not a boundary in some abstract mathematical sense. It is the literal, physical edge of your world, the edge of your reality. And we might be, in cosmic terms, very close to understanding exactly what it means to live this close to it. The story of how humanity discovered this edge is one of the stranger episodes in the history of science because nobody was looking for it. In the spring of 1964, 2 young radio astronomers at Bell Telephone Laboratories in Holmdel, New Jersey, were having a profoundly irritating time with a problem that had nothing to do with cosmology. Arno Penzias was 30 years old, born in Munich to a Jewish family that had fled Germany in 1939, is surviving the pre-war chaos by the skin of their passports. Robert Wilson was 27 from Houston, Texas, with a freshly minted PhD from the California Institute of Technology. They had been given access to a large horn-shaped antenna, 20 feet wide, built originally to communicate with the Echo satellite, and they were using it to study faint radio signals from the edges of the Milky Way. The antenna was the most sensitive radio receiver in the world at the time. That sensitivity was about to become their biggest problem. Wherever Penzias and Wilson pointed the antenna, towards the galactic center, away from it, towards New York City, down toward the horizon, straight up into the sky, they heard a persistent low-level hiss, a uniform background noise with no identifiable source. They checked the equipment systematically and methodically. They pointed at known radio sources, calibrated everything they could think of to calibrate, and the hiss remained. They discovered that a pair of pigeons had taken up residence in the horn of the antenna and had left what Wilson would later describe, with the carefully neutral language of a man writing a scientific paper, as a white dielectric material. They trapped the pigeons, cleaned the antenna, and released the birds. The pigeons came back within the week. They trapped them again, and this time, Wilson recalled years later with a certain dry weariness, the birds were sent to a pigeon farm where they lived out the rest of their days. Or possibly not. Wilson's accounts of the pigeons' final fate have varied over the years, and one suspects the birds did not come back a third time. In any case, the hiss remained. It had nothing to do with the pigeons. By early 1965, Penzias and Wilson had been living with this mysterious noise for the better part of a year. It was isotropic, coming equally from every direction, day and night, summer and winter, regardless of where the antenna was pointed. It corresponded to a temperature of about 3.5 Kelvin, barely above absolute zero, but measurably above it. And then, through a chain of informal scientific communication that says something rather nice about how science actually works, Penzias learned about a preprint paper from a group at Princeton. Robert Dick, James Peebles, Peter Roll, and David Wilkinson were theoretically predicting exactly this kind of radiation as the remnant echo of the Big Bang, a thermal afterglow that had been cooling for over 10 billion years. Penzias telephoned Dickie at Princeton. Dickie listened, asked a few careful questions, and then hung up the phone. He turned to his colleagues in the lab. "Boys," he said, "we've been scooped." The two groups published companion papers in July 1965 in the Astrophysical Journal. Penzias and Wilson's paper bore the exquisitely understated title, "A Measurement of Excess Antenna Temperature at 4080 MHz, and was essentially a list of things that were not causing the noise. The theoretical interpretation was provided by Dickie's group in the companion paper. What Penzias and Wilson had detected, a stumbling through a fog of pigeon drama and antenna calibrations, was the oldest light in the universe. The cosmic microwave background radiation, the thermal afterglow of the Big Bang, emitted when the universe was 380,000 years old, travelling through space for the subsequent 13.8 billion years, and cooling as it went, stretched by the expansion of the universe from visible light into microwaves. It was the furthest thing any human being had ever detected. It was the wall at the back of the observable universe. It was evidence, definitive and incontrovertible, for the Big Bang itself. Robert Dick, whose theoretical work had made the discovery comprehensible, never won the Nobel Prize for it. Penzias and Wilson were awarded the 1978 Nobel Prize in Physics for the detection. Dicker died in 1997. The Nobel Committee does not award posthumous prizes. His name appears in the textbooks, but not on the certificate. Science has a complicated relationship with justice. There is a further layer to this story, one that illuminates how close humanity had come to this discovery before 1965 without realizing it. In 1941, an astronomer named Andrew McKellar measured the temperature of interstellar space using the rotational states of cyanogen molecules in the spectra of stars. He got a value of about 2.3 Kelvin, strikingly close to the actual CMB temperature of 2.725 Kelvin. He published the result without recognizing what he had measured. Robert Dicke himself, working on radar during the Second World War, had measured a microwave background temperature from the Earth's atmosphere and noted it was no more than 20 Kelvin. Then he forgot about it. George Gamow and his colleagues in the late 1940s predicted that the Big Bang should have left a relic radiation field with a temperature in the range of 5 to 10 Kelvin. They published this prediction, but cosmologists of the era were more interested in other problems, and nobody built an instrument to look for it. The CMB was predicted, detected twice without recognition, and finally identified in 1965, partly through coincidence. The universe had been broadcasting on this channel for nearly 14 billion years, and we almost missed the message. Now let us talk about what this wall actually means in terms of scale, because the numbers here require a genuine effort at translation if they are to land with anything other than glazed incomprehension. The observable universe, the sphere of space from which light has had time to reach us since the Big Bang, has a radius of approximately 46 billion light years. Not 13 billion, as you might naively calculate by multiplying the age of the universe by the speed of light. 46 billion. The discrepancy arises because the universe has been expanding while the light was travelling, stretching the distances between everything like dots drawn on a balloon being inflated. The photons that are arriving at our instruments right now from the most distant galaxies were emitted long ago from matter that was then much closer to us. But the expansion of space has carried that matter to its current distance of 46 billion light years. Here is a way to feel the scale. The distance from the Earth to the Moon, that famous voyage, the one that took Apollo 11 3 days to complete, is about 1.3 light seconds. Light covers that distance in the time it takes to say the words 1.3. The distance to the Sun is 8 light minutes. The distance to Neptune, the outermost planet in our solar system, is about 4 light hours. The distance to the nearest star beyond our Sun, Proxima Centauri, is 4.2 light years. So a car journey at motorway speed from Earth to Proxima Centauri, if you had a car that could drive through space and infinite patience, would take roughly 50 million years. The diameter of the Milky Way, our home galaxy, is about 100,000 light years. From one edge to the other of our own galaxy, at the speed of light, would take 100,000 years. Now stack that up. The observable universe is roughly 930 billion light years in diameter. The entire Milky Way, 100,000 light years across, would fit inside the observable universe about 900 million times. The observable universe contains an estimated 2 trillion galaxies. Each galaxy contains, on average, hundreds of billions of stars. Each star is, in principle, a possible host for planets. And the observable universe, vast beyond any reasonable intuition, is itself, based on the geometry revealed by the CMB, a fraction so small of the actual total universe that the fraction is essentially zero for all practical purposes. Conservative estimates, derived from the flatness of the universe's geometry, suggest the total universe is at least 10 to the power of 23 times larger than the observable bubble. and other estimates go further still. If inflation did what physicists think it did, expanding the universe by an enormous factor in the first instant, the total universe may be unimaginably larger. The numbers defy arithmetic intuition. They defy emotional intuition. They simply sit there, immense and irreducible. A scale comparison that sometimes helps. If you were to represent the observable universe as a grain of sand, the full universe, on the conservative estimate, would be represented by a sphere larger than the Earth. If you use more aggressive inflationary estimates, the comparison becomes so extreme as to be meaningless. Our observable bubble is, in every realistic scenario, an astronomically tiny sample of the actual whole. The event horizon is even more striking in its implications for scale. I'm currently sitting at 16 billion light-years, well within our observable universe, and much closer than the furthest things we can see. It marks the absolute limit of any future causal contact. Right now, there are galaxies within our observable universe that we can observe. We can see the light they emitted billions of years ago, but to which we can never send any signal that will ever arrive. We can see them but never touch them, even in principle. They are visible fossils, cosmological ghost lights, and beyond the event horizon, there are regions of the universe that we cannot see, from which we have never received any signal, and to which no signal of ours will ever penetrate. They are as inaccessible as the interior of a black hole, but without the drama of an event. Just the quiet recession of space, faster than light, are carrying those regions permanently out of reach. So how does this work exactly? How can space expand faster than the speed of light without violating relativity? And what does it mean that our region of reality has these hard physical limits? To understand this properly, you need to spend a few minutes with the mechanics of an expanding universe, because the intuition most people bring to this subject is wrong in a specific and interesting way. Albert Einstein published his general theory of relativity in its final mathematical form in November 1915. The theory replaced Newton's view of gravity as a force acting across space with a far richer picture. Gravity is the curvature of space and time caused by the presence of mass and energy. This sounds abstract until you realize that it makes specific, testable predictions. One of the most surprising was that the universe could not be static. Einstein's equations for a universe filled with matter and energy had no stable solutions. The universe had to be either expanding or contracting. Einstein disliked this. It seemed wrong to him. The universe had, he assumed, always existed and would always exist. And so he introduced a term into his equations called the cosmological constant, a kind of built-in repulsion that would balance gravity and hold the universe still. He later described this as his greatest blunder, though there is a certain irony in that description, as we will see. The Belgian priest and physicist Georges Lemaitre derived the expanding universe from Einstein's equations in 1927 and proposed what he called the hypothesis of the primeval atom, the idea that the universe began in an unimaginably dense initial state and had been expanding and cooling ever since. Edwin Hubble confirmed the expansion observationally in 1929 by showing that galaxies were receding from us at speeds proportional to their distances. The further away a galaxy, the faster it was moving away. This relationship, now known as Hubble's law, was the first direct evidence that space itself was expanding. Here is the key conceptual step. Galaxies are not for the most part moving through space. Space is growing between them, carrying them apart the way raisins in rising bread dough drift apart, not by moving through the dough, but by the dough expanding around them. Because it is space that is expanding and not objects moving through space, the prohibition on faster-than-light travel does not apply. Space can expand at any rate without violating relativity. A galaxy at a distance of 10 billion light-years is receding from us at roughly 3 times the speed of light, not because it is unusually energetic, but simply because there is 10 billion light-years of expanding space between us and it, and the expansion of each part of that distance adds up. The Hubble radius, about 14 billion light-years, is the distance at which recession velocities due to expansion reach exactly the speed of light. Galaxies beyond the Hubble radius are receding faster than light can travel toward us through the expanding space between us. You might think this means their light can never reach us. But here is the subtlety that trips up most intuitions. The Hubble radius itself is expanding because the expansion rate is not accelerating fast enough to outrun light at every distance. Galaxies that are currently outside the Hubble radius, receding faster than light, can still eventually send us signals. Because the Hubble radius expands outward as the universe ages and the expansion rate changes, eventually catching up to that light and allowing it to reach us. This is why the observable universe is 46 billion light-years across, even though the universe is only 13.8 billion years old. The cosmic event horizon is a different and more final boundary. It represents the region from which any photon emitted today, pointed toward us, will eventually reach us, given infinite time. Anything beyond the event horizon is receding fast enough, and will continue to recede fast enough, that even light emitted directly at us will never arrive. The event horizon is defined by dark energy. Because dark energy is causing the expansion to accelerate, the Hubble radius is not just staying constant. The effective boundary beyond which we can receive no future signals is gradually moving inward in co-moving terms. More and more of the universe is becoming causally severed from us over time. This is not a temporary situation that better engineering can fix. It is a permanent feature of a universe with a positive cosmological constant, which is what all current evidence suggests we live in. Dark energy itself is one of the deepest mysteries in physics. First inferred from observations of distant supernovae in 1998, work that won Saul Perlmutter, Brian Schmidt, and Adam Rees the 2011 Nobel Prize in Physics, dark energy appears to constitute approximately 68% of the total energy content of the universe. Its effect is to cause the expansion of space to accelerate rather than decelerate. Its nature is completely unknown. In its simplest form, it could be the cosmological constant Einstein introduced and then abandoned, an intrinsic energy density of empty space. Quantum field theory predicts that empty space should indeed have an energy density, arising from the constant quantum fluctuations of all the fields that permeate it. The problem is that the value of this vacuum energy predicted by quantum field theory is approximately 10 to the power of 120 times larger than the observed cosmological constant. This is the most catastrophic quantitative disagreement between theory and experiment in the history of physics. Something is cancelling nearly all of the predicted vacuum energy and leaving only a tiny residual, and we have no idea what that something is or why it does so with such extraordinary precision. Recent data from the DESI experiment, the Dark Energy Spectroscopic Instrument, which spent years mapping the positions and motions of tens of millions of galaxies and published its results in 2024, has added a new wrinkle. The DESI data suggests, with intriguing but not yet definitive statistical significance, that dark energy may not be constant. It may vary over time, weakening slightly over cosmic history. If this finding is confirmed, it will mean that dark energy is not the cosmological constant, but something more dynamic, perhaps a field called quintessence that has evolved throughout the history of the universe. And if dark energy is not constant, then our predictions about the future of the universe, about the fate of the cosmic event horizon, and about the ultimate large-scale structure of reality are all potentially wrong in ways we have not yet begun to quantify. Understanding the cosmological horizon is one thing. Actually studying it is something else entirely, because the barriers to investigation are some of the most daunting in all of science. The CMB marks the furthest we can look in time, the universe at 380,000 years old, the moment it became transparent and light was free to travel. Before that moment, for the first 380,000 years of cosmic history, the universe was a dense, hot plasma that scattered light in every direction like fog. Ordinary photons cannot travel through it. We are looking, when we study the CMB, at a wall of fire, and on the other side of that wall, we are blind. The only tools that might pierce this veil are two things that interact far more weakly with matter than light does. Gravitational waves, ripples in space-time itself, passing through matter essentially unimpeded, were first directly detected by the LIGO Observatory in September 2015, a detection for which Kip Thorne, Barry Barish, and Rainer Weiss received the Nobel Prize in Physics in 2017. Primordial gravitational waves, generated during cosmic inflation in the first fraction of a second after the Big Bang, would carry information from before the CMB wall, from the very first instant of existence. But detecting them requires measuring strains in space-time of roughly 1 part in 10 to the power of 25 or smaller, a sensitivity so extreme that even the quantum noise of the measuring apparatus becomes a fundamental obstacle. The planned space-based LISA mission and next-generation ground-based detectors may eventually reach this sensitivity, but it will require decades of development and unprecedented engineering. Neutrinos present a similar promise. The Big Bang produced an enormous number of neutrinos, as many as photons, and those neutrinos, called the cosmic neutrino background, have been streaming freely through the universe since the first second of its existence. If we could detect them, we would be looking at a snapshot of the universe far earlier than any photograph the CMB provides. The problem is that neutrinos interact so weakly with ordinary matter that capturing them requires detectors of enormous mass and extraordinary sensitivity. The largest neutrino detectors yet built, IceCube at the South Pole, Super Kamiokande in Japan, detect perhaps a few dozen atmospheric or solar neutrinos per day. Detecting the diffuse cosmic neutrino background, whose individual particle energies are far lower than those detectable by current instruments, is a challenge that remains for now beyond reach. Then there is the Hubble tension, a discrepancy that has been deepening for years and may represent the most important unsolved problem in cosmology. When cosmologists measure the expansion rate of the universe using the CMB as their starting point, extrapolating the early universe physics forward to predict what the expansion rate should be today, they get a Hubble constant of about 67 kilometers per second per megaparsec. When they measure it using the local universe, Cepheid variable stars and Type 1a supernovae as distance calibrators, they consistently get a value of about 73 kilometers per second per megaparsec. The difference is about 9%. In a field where measurements are made to fractions of a percent, this is a screaming discrepancy, and either our local measurements are wrong in some systematic way nobody has found despite decades of scrutiny, or our early universe measurements are wrong, or, most tantalizingly, our model of cosmology is missing some ingredient that causes the expansion rate to be different in the early universe than it would be predicted to be today. The JWST is now providing independent distance measurements that are helping to test whether the discrepancy is real. As of early 2026, it has not gone away. Let us go on the journey now. Let us follow the light outward and backward in time until we reach the walls themselves and then see what they are made of. Start from where you are right now. The first thing you would encounter, traveling outward at the speed of light, is the cosmic web, the large-scale structure of the universe, the scaffolding on which everything else is built. Matter in the universe is not distributed uniformly. Under the influence of gravity, it has aggregated over billions of years into enormous filaments and sheets and nodes. Vast threads of galaxies, hundreds of millions of light-years long, connecting at nodes where massive clusters of thousands of galaxies crowd together, separated by vast voids of near-empty space. The largest known structures, things like the Hercules Corona Borealis Great Wall, a complex of galaxies and quasars stretching perhaps 10 billion light-years across, discovered in 2013, are so large they verge on challenging cosmological models that predict uniformity on the very largest scales. Whether these structures are genuinely problematic for the standard model or simply the expected result of statistical fluctuations in an otherwise uniform distribution is still debated. The structures are there, whichever way you explain them. Moving outward and further back in time, you reach the epoch of peak star formation. Between roughly 2 and 4 billion years after the Big Bang, corresponding to a redshift of around 2, meaning the universe has expanded by a factor of 3 since then. The universe was forming stars at a rate perhaps 10 to 30 times higher than it is today. Galaxies were brighter, more violent, and more dynamic, e.g. quasars, active galactic nuclei, powered by supermassive black holes consuming matter at extraordinary rates, blazed across the early universe with luminosities 1,000 times greater than entire galaxies. If you were somehow standing on a planet in that early universe, the sky would have been genuinely extraordinary. The nearest quasar would likely have been visible in daylight, a point of light as bright as the moon. It was the James Webb Space Telescope, launched on Christmas Day 2021, after decades of development and one of the more nail-biting rocket launches in the history of space science, that began truly probing this epoch and beyond with unprecedented sensitivity. Our JWST was designed to see in the infrared, the wavelengths to which visible light from the early universe is shifted by cosmic expansion, and to do so with the kind of light-collecting power that its predecessor, the Hubble Space Telescope, simply could not match. Almost immediately, it began finding things that surprised people. Massive, well-structured galaxies at redshifts corresponding to the universe being only 3 to 500 million years old. Earlier than most models predicted such organized structures could form. Galaxies that should have taken billions of years to build apparently assembled in a few hundred million. Either galaxy formation happened faster than expected, or the initial conditions of the universe were different from what was assumed, or there is physics in the early universe we have not yet correctly identified. The debate is ongoing, active, and productive. Moving further still, you pass through the epoch of reionization, the period roughly between 200 million and 1 billion years after the Big Bang, when the universe's first stars and galaxies switched on and their ultraviolet radiation ionized the neutral hydrogen that had filled the cosmos like fog since shortly after the Big Bang. Before reionization, the universe was opaque to ultraviolet light. The transition from neutral to ionized hydrogen happened patchily, with bubbles of ionized gas growing around the first bright sources until they merged and filled the entire universe. JWST is now probing the boundary of this fog, watching the universe light up source by source. It is, quite literally, watching the universe turn on its lights. The technical challenge of doing this, distinguishing faint signals at extreme distances from foreground noise, accurately calibrating the instruments at the edge of their sensitivity, is extraordinary. But the science being extracted from those measurements is rewriting the early history of our universe in real time. And then you reach the CMB itself, the wall. The photons arriving at our detectors from the CMB were emitted when the universe was 380,000 years old. They carry in their tiny temperature variations, fluctuations of only about 1 part in 100,000, the pattern of density ripples in the early plasma that seeded all subsequent structure. Every galaxy cluster, every filament, every void in the cosmic web was determined, in its statistical properties, by those ancient ripples, which were themselves generated by quantum fluctuations in the first fraction of a second of existence. The CMB is the most precisely measured radiation field in all of science. The European Space Agency's Planck satellite, whose mission ran from 2009 to 2018, and whose final datasets were published in 2020, mapped the temperature and polarization of the CMB across the entire sky with extraordinary precision, constraining cosmological parameters to levels that would have been unimaginable a generation earlier. From that map, we can read the age of the universe, its geometry, the relative densities of ordinary matter, dark matter, and dark energy, the spectrum of primordial fluctuations, and a dozen other quantities. The CMB is a Rosetta Stone for cosmological history, but it also revealed anomalies. A cold spot in the southern sky significantly colder and larger than statistical fluctuations in the standard model can comfortably explain. And a large-scale alignment between the pattern of the CMB temperature fluctuations and the orientation of the solar system, a correlation so striking that it has been nicknamed the axis of evil by cosmologists, frustrated by their inability to explain why the universe's structure should know anything about the plane of the solar system. These anomalies may be mundane statistical fluctuations that will disappear with better data. They may be artifacts of foreground contamination, residual emission from our own galaxy contaminating the CMB signal. Or they may be hints of something genuinely new, topology of the universe, pre-inflationary physics, or even, in the most speculative interpretations, the imprint of a collision with another bubble universe in the inflationary epoch when our cosmos was born. Beyond the CMB wall, in those opaque first 380,000 years, lies the inflationary epoch, the theorized period when the universe expanded by a factor of perhaps 10 to the power of 26 in less than 10 to the power of minus 32 seconds. Inflation was proposed in 1980 by Alan Guth, then a young postdoctoral researcher who had been working late at night in his office at Stanford, chasing a solution to several deep problems in the standard Big Bang model. Why was the CMB so uniform? In the standard Big Bang, the patches of the sky on opposite sides of the CMB were never in causal contact. They were too far apart to have exchanged any information by the time the CMB was emitted. How could they have reached the same temperature? Why is the geometry of the universe so close to flat? The density of the universe must be tuned to extraordinary precision to produce a flat geometry. Slightly too much, and the universe collapses. Slightly too little, and it expands too fast for structures to form. And where were the magnetic monopoles that grand unified theories predicted should have been produced in enormous quantities at high temperatures in the early universe? Nobody had ever observed one. Inflation solved all three problems simultaneously, which is the kind of theoretical economy that physicists find deeply convincing. If the universe underwent a brief, violent period of exponential expansion in the first instant, any initial curvature would be flattened out. any monopoles would be diluted to undetectable densities, and the regions we observe in opposite directions in the sky would all have originated from the same tiny patch of the primordial universe in causal contact before inflation blew them apart. Furthermore, quantum fluctuations in the inflaton field during inflation would have been stretched to cosmic scales, seeding exactly the pattern of density fluctuations we observe in the CMB. The key smoking gun evidence for inflation, the signature of primordial gravitational waves in the polarization of the CMB, a distinctive pattern called B modes, has not yet been detected. It is the primary target of the next generation of CMB experiments. Finding it, or setting strong enough limits to rule out the simplest inflationary models, is one of the great outstanding goals of observational cosmology. Now here is the pivot. Here is the moment where everything looks slightly different than it did. Throughout this exploration, there has been an implicit assumption at work that what we have mapped and measured and understood represents a reasonable sample of what there is to know. The CMB constrains cosmological parameters to a few percent. The cosmic web is statistically characterized across billions of light years. The history of the universe from the first second to the present is modeled with extraordinary precision. We have a standard model of cosmology, lambda CDM as it is called, as for the cosmological constant lambda and cold dark matter that fits essentially all available data to remarkable accuracy. We know, we think, roughly what we are dealing with. Here is what that confidence actually represents. Everything we have ever observed, every photon detected by every telescope, every particle detected by every particle detector, every gravitational wave detected by LIGO and Virgo and the other interferometers, all of it comes from within the observable universe. That bubble of 46 billion light-years. And that bubble represents, by the most conservative geometric estimates based on the flatness of the CMB, at most something like 10 to the power of negative 23 of the actual volume of the universe. 1 divided by 100,000 billion trillion. Our entire observable cosmos, with its 2 trillion galaxies, its cosmic web spanning billions of light-years, its extraordinary measured precision, is a sample so vanishingly small that drawing universal conclusions from it is less reliable than trying to characterize the entire Atlantic Ocean from a single teaspoon of water. Here is an analogy that captures this more viscerally. Imagine you have been tasked with writing the definitive natural history of the entire Earth. Every species, every ecosystem, every geological formation. You have been given one instrument, a single pinhole camera that shows you a circle of ground 1 centimeter across. The circle moves slowly across the ground at random intervals, pausing for observation, then moving. You study the circle. You measure its contents with extraordinary precision. You model the biology and chemistry of what you find there with great sophistication. You publish your results in leading journals. Now someone asks, but what does the rest of the Earth look like? The honest answer is, you don't know. You can make inferences based on physical laws you have established and the statistical properties of your sample. But you cannot know. The entire cosmos we have mapped, measured, and modeled is that 1 centimeter circle, and the rest of the Earth, the oceans, the mountains, the rainforests, the deserts, the ice caps, the depths of the ocean trenches, is the unobservable universe, permanently beyond your pinhole. This is not merely a matter of needing better telescopes. The JWST, the CMBS-4, the Square Kilometre Array, all of these will extend our sample, push our measurements to higher precision, and constrain our models more tightly. They will not, cannot reach through the event horizon. They cannot tell us what is happening right now in the regions of the universe that crossed the event horizon 10 billion years ago. They cannot tell us whether the physical constants are the same out there, whether dark energy has the same value, whether inflation produced a universe that is simply very large or truly infinite. The walls of the observable universe are not walls we can chip away at with better tools. They are walls written into the laws of physics, and they will stand as long as those laws hold. The picture this paints of the human scientific enterprise is at once humbling and exhilarating. We have, in roughly 400 years since Galileo pointed a telescope at Jupiter's moons, built a detailed and mathematically precise picture of the universe, from the Planck scale to the Hubble scale. We have measured the age of the cosmos to within a few percent. We have identified the major components of its content. We have traced its history from the first second to the present day. We have detected ripples in space-time from colliding black holes 1 billion light-years away. These are staggering achievements, unparalleled in the history of any civilization on Earth, and for all we know, in the history of the universe. And what they amount to is this. We have very, very carefully described one grain of sand, and the beach extends beyond the horizon in every direction, and we cannot go there. The cosmic event horizon is not the furthest point we have managed to explore. It is the furthest point that is, in principle, explorable, and it sits only 16 billion light-years away, less than half the radius of what we can currently see. Everything beyond it is not merely unexplored, it is permanently, physically unreachable. The universe is not a place that will eventually yield its full secrets to sufficiently determined inquiry. It is a structure with a hard information limit, and we sit well inside that limit, looking outward at walls we will never cross. Consider what has been accomplished in comparable endeavors. The Apollo program, the entire 12-year effort from Kennedy's 1961 speech to the last moon landing in 1972, landed 12 human beings on the surface of the moon, a celestial body 384,000 kilometers away, and returned them safely to Earth. At the speed of Voyager 1, the fastest object humanity has ever launched, it would take that spacecraft approximately 73,000 years to travel from Earth to Alpha Centauri, the nearest star system. The cosmic event horizon is roughly 6 million times further away than Alpha Centauri. The actual edge of the observable universe is 27 million times further. The actual extent of the total universe, if it ends at all, is beyond any number that connects meaningfully to human experience. And yet, the Planck satellite, orbiting the Sun from a distance of about 1.5 million kilometers, produced a map of temperature variations in radiation that was emitted 13.8 billion years ago from the edge of our observable cosmos. And from that map, scientists derived the age, geometry, and composition of the universe to percentages. The JWST, orbiting the same point as Planck, is photographing individual galaxies in the first few 100 million years of cosmic history. The LIGO detectors, sensitive enough to measure a change in length 1/10,000th the diameter of a proton across a 4-kilometer baseline, have detected gravitational waves from black hole mergers at cosmological distances. This is the most precise measurement ever made in the history of science, applied to the oldest signal ever detected. What we are doing is extraordinary. The scale of what we are doing it in, compared to the scale of what there is simply humbling. What discovery at the frontier of this science could mean for humanity is worth dwelling on. Finding the signature of primordial gravitational waves in the CMB would, at a stroke, and confirm inflation and give us our first direct empirical window into the first instant of the universe. Physics at energies 1 trillion times higher than any particle accelerator can reach. Resolving the Hubble tension would either reveal new physics in the early universe or identify a systematic error in our distance measurements that has contaminated a generation of cosmological conclusions. Understanding the nature of dark energy, whether it is truly a constant or something dynamic or a signal that our theory of gravity needs modification, would transform our understanding of the universe's fate and possibly reveal new physics that connects the very small and the very large in ways currently beyond our reach. But there is something more fundamental at stake than any specific discovery. We are the only species, as far as we know, that has ever looked up at the night sky and asked not just what is up there, but what the edge of up there looks like and whether up there ends, and what it means that it does or does not. The cosmological horizon is not just a physical boundary, it is a philosophical one. It marks the edge of what any intelligence, anywhere in the universe, can ever know about the universe as a whole. And the fact that we are standing here at this particular moment in cosmic history, early enough to see the large-scale structure before it recedes beyond the event horizon, late enough to have the tools to measure it, is either a remarkable coincidence or, as some cosmologists have suggested half seriously, a hint about the kind of universe that can support observers in the first place. The edge of reality is not distant. It surrounds us at 46 billion light-years in all directions, and it is getting closer in the ways that matter every day. We might be nearer to understanding it than any humans have ever been. And that understanding, partial, bounded, humble, and expanding, is among the most remarkable things our species has ever achieved. The conspiracy theories that have grown around the cosmological horizon deserve a moment of honest examination, because some of them originate from a legitimate discomfort with the science. The most persistent is the idea that the observable universe's limits are artificial, not a consequence of physics, but of deliberate concealment, a kind of cosmic curtain drawn by powers unknown, whether those be governments, shadowy scientific elites, or, in its most elaborate form, the operators of a simulation. The simulation hypothesis, the idea that our entire reality is a computer program running on hardware we cannot access, has been seriously discussed by philosophers and physicists as a genuine possibility rather than science fiction, most notably by the philosopher Nick Bostrom, whose 2003 paper on simulation arguments laid out the logical structure of the idea with some care. If the universe is a simulation, the cosmological horizon could, in principle, be the rendering limit, the edge beyond which the program does not bother to generate detail. The horizon would be not a physics fact, but an engineering choice. This is, in its way, an interesting idea. But the scientific case against it is straightforward and does not require appeals to parsimony or taste. The cosmological horizon is not a fixed wall at a convenient distance. It is a dynamic, physically derived boundary that follows precise mathematical relationships based on the speed of light, the age of the universe, and the measured rate of expansion. Its position matches, to extraordinary precision, the predictions of a standard cosmological model calibrated entirely from independent measurements. If it were an artificial rendering limit, it would have to be fake rendered in a way that is consistent with the CMB temperature, the large-scale structure, the abundance of light elements, the rate of cosmic expansion, the properties of dark matter and dark energy, and dozens of other independent constraints, all pointing to exactly the same history. A simulation sophisticated enough to fake all of that is indistinguishable, by definition, from the real thing, which means the question becomes philosophically interesting and scientifically inert. You cannot test it. A related fringe idea, somewhat more grounded, is that the universe is not as large as mainstream cosmology suggests, that the CMB anomalies, the cold spot in particular, indicate that the universe has a smaller, finite topology that we are somehow wrapping around. In a universe with a sufficiently small spatial topology, you might look in one direction and, if the universe is small enough, be seeing the back of your own head, cosmologically speaking, your own observable bubble tiling through space. Some cosmologists have genuinely explored this idea, looking for matching patterns on opposite sides of the CMB sky. So far, the data does not support it, but it remains a legitimate, if disfavored, scientific hypothesis. Unlike the simulation theory, it is actually testable, and tests have been done. The universe does not appear to be small enough for its topology to be directly observable. The most spectacular fringe claim surrounding the cosmological horizon is perhaps the multiverse interpretation. The idea, arising from inflationary cosmology, that our observable universe is just one of an enormous or infinite number of bubble universes, each with potentially different physical constants, each separated from all others by expanding inflationary space, each forever beyond the event horizon of all the others. This is not, strictly speaking, a conspiracy theory. It is a mainstream theoretical consequence of the most widely accepted model of inflation. What makes it controversial is that it is, under most formulations, untestable. If all other universes are beyond our event horizon, by definition, they cannot be observed. The multiverse is theoretically motivated, logically coherent, and possibly real, and also, in the strict Popperian sense, currently unfalsifiable. This sits awkwardly in a science that prizes testability. String theorists have argued it is the most natural outcome of the landscape of string vacua. Others have argued, with some passion, that a theory that cannot in principle be tested is not physics but metaphysics. The debate has not been resolved. It may not be resolvable with current methods. What all of these ideas share, the simulation hypothesis, the compact topology, the multiverse, is that they are responses to a genuine, vertiginous feature of our situation. We live inside a bubble of knowable reality, and we cannot get out. That discomfort is real, and it is intellectually honest. The question is whether you respond to it with testable science, with philosophical speculation, or with elaborate mythology. The best cosmologists do the first, acknowledge the second, and gently decline the third. Now consider the future in concrete terms. In approximately 150 billion years, if dark energy continues its current behavior, all galaxies outside our local group will have crossed the cosmological event horizon. The sky of any astronomer alive at that epoch, assuming any are alive, which seems optimistic given that the Sun will have died some 90 billion years before, will show nothing but the Milky Way and its nearest neighbours. No spiral galaxies in Virgo, no quasars at the edge of the observable universe, no CMB. The CMB will have cooled far below any detector's threshold. The large-scale structure that took billions of years to map and understand will be completely invisible. The only evidence that other galaxies ever existed will be in whatever physical archives have survived from a time when the cosmic web was observable. If those archives are lost, any future observers will be trapped in an apparently static universe of a few dozen galaxies, with no evidence from observation alone that the cosmos has any larger structure. They will be wrong about everything they think they know about the scale of reality, and they will have no way to discover their error. We are fortunate, with a luck that has nothing to do with desert or merit, to be alive at the only epoch in cosmic history when the large-scale structure of the universe is still visible and warm enough to be studied with the instruments we have. We are cosmologically privileged observers. The window is not closing quickly. It will remain open for tens of billions of years. but it is closing. And the awareness of that closing, the understanding that our descendants in the very far future will inherit a cosmologically impoverished universe, with fewer observable galaxies, less accessible information about their history, a darker and colder sky. That awareness is perhaps the most poignant thing that cosmology has to offer. The universe is generous to observers who exist now. It is less generous to those who will exist later. There is one more aspect of the deep physics of the horizon that deserves careful explanation, because it connects the local and the cosmic in a way that changes how the entire picture feels. The cosmological event horizon is not just an abstract boundary far away in space. It is, in a mathematically precise sense, the cosmological analogue of a black hole's event horizon, and it has similar thermodynamic properties. Stephen Hawking showed in the 1970s that black hole event horizons are not perfectly black. Because of quantum mechanical effects near the horizon, black holes slowly radiate thermal radiation, Hawking radiation, with a temperature inversely proportional to their mass. The smaller the black hole, the hotter it radiates, until eventually it evaporates entirely. This was one of the most profound theoretical discoveries in 20th century physics, connecting thermodynamics, quantum mechanics, and general relativity in a single result. The cosmological horizon has an analogous property. Gibbons and Hawking showed in 1977 that an observer in a universe with a positive cosmological constant, a universe like ours, is surrounded by a cosmological event horizon that has a temperature. The temperature is extraordinarily small. For our horizon, it is roughly 10 to the power of -30 Kelvin, far colder than the current CMB temperature of 2.725 Kelvin, and so cold as to be physically irrelevant for any process occurring in the current universe. But as the universe expands and cools, as the CMB redshifts to ever lower temperatures, eventually the cosmological horizon temperature will become the dominant thermal background. The universe's ultimate thermal floor is not absolute zero. It is the temperature of its own horizon. And this temperature, small as it is, has profound implications for the ultimate fate of information in an accelerating universe. A problem that connects directly to one of the deepest unsolved questions in theoretical physics: whether information is truly preserved in quantum mechanics, or whether the universe has a mechanism for destroying it. The specific details of how information behaves at cosmological horizons connect to the broader black hole information paradox. The question of whether information falling into a black hole is truly lost, or whether it is encoded in the Hawking radiation that the black hole emits as it evaporates. This question was vigorously debated by Stephen Hawking and John Preskill in a celebrated bet made in 1997. Hawking argued information was lost. Preskill argued it was preserved. In 2004, after years of theoretical work by Leonard Susskind, Juan Maldacena, and others, Hawking conceded the bet, paying Preskill with a baseball encyclopedia, the canonical repository of statistical information, on the grounds that information could be retrieved from a black hole, though in a mangled form. Whether the same applies to cosmological horizons, whether the information about the galaxies that have crossed our event horizon is somehow encoded in the radiation our horizon emits, is an open question that sits at the intersection of quantum gravity, thermodynamics, and cosmology, in a region of theoretical space where our understanding is genuinely incomplete. The Hubble constant itself deserves a moment of closer examination, because it is the quantity that determines where the horizon sits, and the fact that we cannot agree on its value is more unsettling than it might initially appear. The Hubble constant, measuring how fast the universe is expanding, has been contested throughout the history of observational cosmology. Edwin Hubble's original 1929 measurement gave a value of about 500 kilometers per second per megaparsec, which implied a universe only 2 billion years old, younger than the Earth, as geologists of the time immediately pointed out. Subsequent improvements brought the value down to the 67 to 73 range we are arguing about today. But the current tension is different in kind from historical measurement uncertainties. Both sets of modern measurements have been made with extraordinary care by separate groups using independent methods, and the results persistently disagree. It is not a matter of one team being sloppy. Something is genuinely wrong with our picture, and we do not know what. The most intriguing proposed resolutions involve new physics in the early universe, a brief period of early dark energy that temporarily boosted the expansion rate before recombination, or new light species beyond the standard model of particle physics that altered the sound horizon in the CMB plasma. Some proposals involve modifications to gravity itself. Perhaps general relativity is not quite the right description of gravity on the larger scales, and a modified theory would naturally produce the observed tension between local and early universe measurements. The JWST has been examining Cepheid variable stars, the traditional rungs of the cosmic distance ladder, with a precision that Hubble could not match, and so far has confirmed rather than resolved the tension. The universe is stubbornly refusing to agree with itself, and the reason is not yet known. Beyond the immediate mysteries of dark energy and the Hubble tension lies a question that cosmologists rarely discuss in public, because it is embarrassing in the specific way that all fundamental incompleteness is embarrassing. We do not actually know what happened at the Big Bang. We have a model that works from about 1 second after the Big Bang to the present day with extraordinary accuracy. We have inflation to fill in the first tiny fraction of a second. But the very first instant, the transition from nothing to something, or from a previous phase to the current universe, or from whatever existed before, is genuinely beyond our current physics. At the Planck scale, roughly 10 to the power of minus 43 seconds after the Big Bang, quantum gravitational effects become dominant, and our best current theories, general relativity and quantum field theory, simply break down. They produce infinities, absurdities, predictions of zero probability for observable events. The physics of the Planck era requires a theory of quantum gravity that we do not yet have. String theory, loop quantum gravity, and various other candidates have been proposed. None has produced a definitive, or experimentally confirmed prediction about physics at the Planck scale. We are, at the moment of most extreme importance, the origin of everything, completely at sea. This is the genuine scientific humility that the cosmological horizon demands of us. Not false modesty, not performative uncertainty, but the honest acknowledgement that the largest questions we can ask, what is the universe? How did it begin? Where does it end? How does it end? Remain in their deepest forms unanswered. The answers we do have are real, precise, and extraordinary, but they are answers to questions about a tiny fraction of the total structure, derived from observations confined to a negligibly small sample, constructed on theoretical foundations that we know, with certainty, are incomplete. The universe's frontier is not a distant place. It is everywhere, as close as the edge of what can be known, as immediate as the light arriving at your eyes from the faintest, most distant galaxies that JWST has managed to photograph. We are, every one of us, inhabitants of a bounded territory of knowable reality, surrounded by an immensity that physics tells us is real, and that the same physics tells us we can never reach. That is the most honest thing that cosmology has ever told us. It is also the most interesting. There is a thought that comes when you sit with all of this long enough, and it deserves to be stated plainly. The James Webb Space Telescope's most distant confirmed galaxy, discovered in 2024, and designated JDES GSZ 140, existed when the universe was only about 290 million years old. It is so far away that its light has been travelling for roughly 13.5 billion years. It is visible, studied, understood in its broad outlines. A massive galaxy that should not exist at that epoch, busily defying our expectations, roughly 15 billion times the mass of the Sun, present and active in the first 3% of cosmic time. And yet, from that galaxy's perspective, if we can imagine such a thing, we are equally remote, equally ancient, equally surprising. The universe they would observe, if anyone were there to observe it, would be just as carefully structured and just as impenetrable at its edges as the one we see from here. Every observer, in every galaxy, in every corner of the cosmos, is surrounded by their own sphere of knowable reality, bounded by the same physics, subject to the same hard limit, looking outward at walls they cannot cross. The cosmological horizon is democratic in the most profound sense. It is the same for everyone. The edge of reality is not a place you can visit or a thing you can photograph. It is a relationship between observers and the universe that contains them, defined by time and the speed of light and the relentless expansion of space. We are, each of us and all of us together, at the center of everything we can ever know, and at the edge of everything else. That is the most extraordinary geographic fact in the history of the universe. We are here, we can see this far, and then there is a wall. And the wall tells us something true and important, that the cosmos is larger than thought, stranger than imagined, older than the oldest story, and richer in its silences and its limits, than any answer we have yet been clever enough to find. We are in the rare and perhaps unique position of being a species intelligent enough to recognize the limits of its own knowledge, precise enough to measure exactly where those limits are, and honest enough, at least in our best moments, to say, beyond here, we do not know. That combination of capability and humility is perhaps the most human thing about us.